couple of examples using the integral test for conversions. So with our first example, we see that we have the series where the general term is 1 over n times the square root of n. And then the second example is just going to be 1 over n. All right, so we're going to look at the kind of like the difference between the two. So the idea is we need a function which is the equivalent of our general term of the series. So we are looking at f of x is going to be equal to 1 over x times the square root of x. Right. Now, if this function is continuous, positive, and decreasing, then we can perform the integral test. Right. So a quick check on our graphing calculators, and we see that this function actually is continuous, positive, and decreasing for x greater than or 1. Right, and you can check that out on your own. You can pause the video if you want to check that on your calculator. But we'll see that this is one of those functions where, actually, just graph right up here, when the positive function, we have that kind of situation happening. So it's quite often like 1 over x, or 1 over, in this case, it's going to be 1 over x to the 3/2 that we'll see in a moment, or e to the opposite of x. All right, we need functions that are positive, decreasing, and then, of course, continuous. Okay, so we can perform, therefore, the integral test, which says let's take the integral as x approaches. Basically, what we're going to do here is we're going to take the integral as from 1 to infinity dx. That's what our goal is right there. Okay, we can actually antiderive that term, but we know that because it's an improper integral, we're going to need to use our appropriate notation, which is the limit notation. So we have to set that up first. And in doing so, we're looking at the limit as b approaches infinity of the integral from 1 to b. And again, up here, this is really 1 over n times n to the half. And we can add in our exponents. We have n to the 3/2, which we know is n to the negative 3/2 once we move that term up into the numerator. So the same thing's going to be happening right here, just be in terms of x. So we have x to the negative 3/2 dx. Right? So if we can calculate the value of that integral right there, if we can determine that this integral converges, then that means that the series is going to converge. Right? So let's go ahead and find this and this integral if possible. So we know the antiderivative of x to the negative 3/2 is x to the negative 1/2. So we're looking here at the limit as b approaches infinity of x to the negative 1/2 over negative 1/2 being evaluated from 1 to b. And that means we have the limit as b approaches infinity. If we're dividing by negative 1/2, that really means we're multiplying by negative 2. So we get negative 2. And then this is x to the negative 1/2, but we can move that into the denominator, make it x to the positive 1/2. And then x to the half we know is the square root of x. So we really have this right here. And again, that's being evaluated from 1 to b. So our first number that we plug in is b there. So we have the limit as b approaches infinity. And I'm actually going to need some braces here. So we have negative 2 over the square root of b minus negative 2 over the square root of 1. And negative 2 divided by the square root of a very large number is going to be 0, minus, and then negative 2 divided by the square root of 1 is negative 2. So 0 divided by, minus negative 2. So our improper integral converges to the value of 2. More importantly, that improper integral converges. And since the improper integral converges, that means that our series must converge as well. So this is yes, it does in fact converge. Okay. Now just be careful. You notice that the bullet points at the bottom of the page there. Just because the integral converges to 2 does not mean that the series will converge to 2. 2 is actually the upper bound of what the series could actually converge to. Okay, but not the same value. Okay, it's just the upper bound of the values. All right. Let's compare this problem with this one over here, which is our harmonic series. Now we took a look at the alternating harmonic series in the just previously using our alternating series test. But what we have here now is just the regular harmonic series. We're going to follow the same pathway that we did right here. All right. So what we're ultimately setting up is the integral from 1 to infinity, and again, this 1 matches with that 1 right there, of 1 over x dx. And this integral we can go ahead and find, because again our conditions are that the function must be continuous on the interval, and from 1 to infinity the function is continuous. The function must be decreasing, and the function must be positive. And again, our curve is looking like that, so this falls in the category of acceptable to be able to use the integral test. All right, so let's go ahead and do that. We have the limit as b approaches infinity of, we know what the antiderivative of 1 over x is. That is the natural log of the absolute value of x, and that's being evaluated from 1 to b. All right. And now we can plug in our values using our fundamental theorem of calculus. So we have the limit as b approaches infinity of the natural log of b minus the natural log of 1. I can lose the absolute value since b and 1 are both positive. Right? The natural log of b, where b is heading towards infinity, that does not exist. All right, so even though we're subtracting 0, we still have a really large number minus 0, which is the really large number. So this does not exist, which means that since the improper integral diverges, our series diverges as well. So the alternating harmonic series will converge. The harmonic series, though, diverges. That's very important for us to realize that and for us to use that, because that's going to come up multiple times in our upcoming lessons. It comes up when we're looking at the bounds, rather the endpoints of our what's known as an interval of convergence for our power series. And we can also use the fact that the harmonic series diverges along with some future tests, the direct comparison test, the limit comparison test, in order to determine whether or not other series will converge or diverge, as you'll see in upcoming videos.